Okay, good morning. So let us continue the lesson. So far, if you remember, we talked about the notion of the derivative. We learned that a particular type of limit is important, and then we call that the derivative, do you remember? So we learned that, for example, for finding the instantaneous speed of a moving particle or to find the slope of the tangent line, we learned that this type of limit is important, and we have some applications for that limit. So because then it appears in many places in mathematics, we gave it a name, and then we try to investigate the properties of this particular limit, and then we learned how to find the derivative of a function through the process of differentiation. I give you a function, then you do some process on it, which is called differentiation, and you reach to a function that is called the derivative of your function. And in the previous lesson, we also talked about primitive functions. So it means that now the final process is given to you. You want to go backward and find the original function. Instead of calling it original function, we called it the primitive function. Yes? Up to this point, finding the primitive function is just probably a game or a mathematical curiosity. So is it possible, if I give you the final processed function, that if I give you the derivative, can you go back to the original function? So far, that is just a mathematical curiosity. We don't have that much motivation why this game, if this is a game, is useful. Yes? Now I want you to momentarily forget about what you have learned about primitive functions. Just focus on something new, which we will call it integrals. And then I want to motivate you why another type of limit becomes important in mathematics. And then again, exactly like what we did for derivatives, we will see that this type of new limit that I want to present for you today also appears in many places in mathematics and physics, engineering, and any kind of applications. So then again, it deserves a name from a mathematical point of view, and it deserves to be investigated to find the properties, yes, of that limit. But for the time being, I start the motivation of this limit by designing this question. Actually, it's a very simple question. So we have a function, f of x is equal to x squared plus 1. I have intentionally have different scales on the x and y axis to make it more transparent. So this is just a parabola which has been shifted 1 unit upward. That is just the normal y is equals to x squared function, which is supposed to be a parabola passing through the origin. But because of this 1, I have shifted it 1 unit upward, and then I don't need the left-hand side, so I didn't care about the left-hand side. I want to focus only on this portion of the graph between 0 and 2. Yes? So you see that if I put 1 in the function, then the answer will be 2, and if I put 2 in the function, the answer will become 5, and if I put 0, the answer becomes 1. So that is just a very simple function, f of x equals to x squared plus 1. The motivating question here is that I want to find this area. Yes? So I want to find the area which is confined between these vertical lines, the horizontal x-axis, and this curve, which is x squared plus 1. So we want to find the area here, of this region, yes? Between these two straight vertical lines, this straight line, which is the x-axis, but this part is a curve. Of course, and then probably you know that finding an area is actually very important. For example, if you have a piece of land, if it is a polygon, you don't have any problems with finding the area, yes? Because you can partition your polygon to triangles, and you already know how to find the area of each one of those triangles. And after that, you add them up, and you get the area of your polygon, yes? But the problem is that what happens if I have a curve? So what happens if I have a region bounded by curves? Yes? Then I want to find the area. Of course, one of the very famous one you already know, and that is the area of the circle. But probably you haven't seen the proof of that yet, because more or less it will go through this process. So the only curve, the only region with curve boundary that you can probably find its area exactly is the circle so far. Yes? And then probably, I don't know if you have heard about the ellipse or something. But for the time being, if I want to find the area, let us see what we can do. Actually, the process was discovered by Archimedes, actually. So mainly the question of integral historically goes before the derivative. And actually they seem totally unrelated, yes? So the notion of the derivative gives you somehow the slope of the curve, yes? But now I am trying to ask you another different question. What is the area below this curve? So apparently they are really totally unrelated. And that was the genius of Newton who discovered the relation between these two concepts. Okay, so I want you to try to understand what is going on. This part is somehow in the book, but probably it is not that important for the exam. This one I want you to understand, otherwise you just do the calculations without understanding what you really do, okay? So if you want, so the point is that I want to find that area. One idea is to start approximating this area by the shapes that we already know how to find the area for, yes? For example, you can say that, okay, between these two numbers from 0 to 2, I take the minimum value for my function, and then I construct a rectangle on it. Yes? And if I ask you, can you calculate the area of this rectangle? The answer is yes. And it is very simple. Okay? So you might say that the area that I am looking for, let me call it area A. So area is the area that I am targeting to find its value, is equal to the area of this rectangle, which is 2 in length and 1 in height. So this becomes just 2 times 1, which is 2. Of course, if I put equality, you do not buy this equality because it is clear that is not exactly the area that I'm looking for, yes? So if I calculate the area of this rectangle, it's actually much lower apparently than the area that I'm targeting. This means that I am just ignoring this part. So this is not a good idea to write equality, so I would say this is approximation. It's not probably a very good approximation at all. But the point is that now, instead of considering only one rectangle, let me consider 2 rectangles. So it means that from 0 to 2, I divide my interval to 2 equal pieces and do this process that I described here for one interval for each one of these subintervals. So it means that momentarily focus here between 0 and 1, and then find the minimum value of your function here, so which is this length, and make a rectangle here, but up to this point, okay? And then forget about this part and focus here and do the same thing here. So now on this interval, the minimum value is this one, so I construct another rectangle here, yes? So then I have 2 sub-rectangles, yes? And now if I ask you, what is the area of this rectangle? The answer is easy. This is 1 unit. This is also 1 unit. So this becomes 1 times 1 plus. And if I ask you what is the area of this rectangle, then you would say that the width is actually 1. What is the height? The height is how much? The height is 2. Yes? So then it becomes 1 times 2. And if I add them up, it becomes how much? 3. So then it's still, can I say this is equal? No. I should say A is approximately equal to 3. Why? Because I am not considering this part. I am not considering this part. I am not considering this part. So if I add these two numbers, it becomes approximately equal to the area that I am trying to find. But I hope that you agree with me, this is a better approximation than the previous one. That is the whole point. Is that understandable? So when I approximated my area with just one rectangle, the error that I make is this much. Yes, this was the error. But now how much error that I am making right now, this part is the error that I'm not considering, plus this part that I'm not considering. I hope that you agree with me. The sum of these two errors are smaller than the previous error. So that is the motivation behind that. Yes? So this means that if I say the area is 2, this is not okay. If I say the area is 3, it is not okay. But what is clear is 3 is a better approximation to the area that I am targeting to find than the previous value. Is that clear? So that is the idea. Okay, so then I think it is very easy to understand yourself. If I want to make my approximation better and better, what should I do? I need to increase these subintervals. Yes, the number of subintervals. So let us just clean this one again. For example, let me consider, 3 is not a good number because I cannot divide 2 by 3. Let us jump immediately to 4 rectangles. So if I want to do it with 4 rectangles, so it means that I have to partition this interval to 4 equal pieces. So this would be the midpoint and this would be the midpoint. Okay, what I do, I will do the process once for each one of these subintervals. So it means that let us focus between 0 and 0.1, 0.5, and then find the minimum and make your rectangle here. Yes, so this is your rectangle here. You see that I have made an error here, and that is a little bit smaller than the previous one. And then what I do for this one, I find the minimum value on this interval, which is this length, and on top of that, I construct a rectangle. Yes, and I go to the next interval from 1 to 3 over 2, and then what is the minimum value is this one, so I construct a rectangle on top of that. Yes? And then I go to the next interval, yes, and I find the minimum value, which is this one, and then I construct a rectangle on that. So if I want to show the error for you, to highlight the error, this is one part of my error, this is another part of my error, and then if this is another part, and this would be another part. Yes, so if I ask you how you calculate the area using this new approximation, you calculate the area of each one of these and add them up. Yes, so what will happen here, the area is approximately, again, equals to the area of this rectangle, which is 0.5 times 1, plus the area of this one is also let me write 0.5 on the right hand side. So it becomes 1 times 0.5 plus, here, how much I have? Okay, can you tell me? The width is still 0.5. Okay, but can you tell me what is the height here? So what's the height? So you need to put 0.5 where? Because you want to find the height. This point is on your graph, yes? And then you want to find the height corresponding to 0.5. So it means that you need to take 0.5 and put it in your function. What you get is the height. Yes? So let me just do that here for you. So I would say something like this. So A is approximately, let me go here to make it clear. A is approximately equal to, the first one is 1 multiplied by 0.5. The next one is what? If I ask you where did I, of course it was very simple to read it 1, but what is 1 actually? 1 is f of 0, yes, multiplied by 0.5. Do you agree? If I ask you this height, of course this is very easy to see it in the picture, it is 1, but if I want to calculate 1, this number is 0, I put 0 in my function, what I get is the height. Yes, so this is f of 0 multiplied by 0.5 plus, if I go to the next rectangle, the width is still 0.5, but the height is the value of my function at 0.5. Yes, so I can write it as f of 0.5 multiplied by 0.5. Yes, and let us go to the next one. Can you tell me what is the next one? If I want to write it similar, what is the area of this rectangle? If I want to write it like that. So you need to take the width, which is still 0.5, but multiply it by the height of that triangle. But can you tell me what is the height of this triangle? Of course, it is easy to read it here. It's 2. But in general, if I want to calculate the height, what I'm supposed to do, I have to feed in this 1 into my function, then I will get the corresponding height. Yes? So then it becomes f of 1 multiplied by 0.5. Then the last one, again, the width is 0.5. What is the height? Can you tell it to me? So what is the height? F of what is the height? So if you don't mind, let me, of course I have already written that 0.5, and then what is this number here? 1.5. Yes? And if I want to find the height, this is f of 1.5. So first of all, I want to give you time. Do you understand what is going on? Yes? Do you agree that if I start calculating this number, this becomes close to the area that I am trying to find, but not exactly? Yes? Is that clear? Yes or no? Okay, let us try to a little bit calculate this. So now this one is equality. This one is approximately equal to this, but this one is exactly equal to the one that I'm supposed to calculate. So f of 0 is 1. F of 0, you put 0 here, you get 1. Multiplied by, let me write it in fraction form. Yes, 1 over 2. Plus f of 0.5. It means that I have to plot 0.5 here. 0.5 is 1 over 2. I put 1 over 2 here, it becomes 1 over 4, and then I have an extra 1, so this becomes 5 over 4. So this number is 5 over 4, and then I have multiplied by 0.5. Instead of 0.5, let me write 1 over 2 again. And then what is f of 1? I have to go to my function, replace x with 1, it becomes 1 squared plus 1, which is 2, multiplied by 1/2. And then finally I go to here. 1.5 is 3 over 2. I put 3 over 2 here, it becomes 9 over 4. And then I have extra 1. If I add them, it becomes 13 over 4. So then it becomes 13 over 4 multiplied by 1/2. And I have to calculate this. Okay, and then if you see 1 over 2 is common, so let me factor it out. So it becomes 1 plus 5 over 4 plus 2 plus 13 over 4 and times 1 over 2. So 5 over 4 plus 13 over 4 is 18 over 4, which is how much? Is 9 over 2 and plus 3. So it becomes 15 over 2 times 1 over 2. So it is 15 over 4. Okay, let me double check. So this is 9 over 2 plus 3, 6, 15, yes. And then it was 15 over 4. So you see, the first approximation was 2. The second approximation was 3. The third approximation is 15 over 4, which is how much? 3.75 or something. Yes? So you see, this number is more reliable than the previous number when it comes to the area. I just want you to understand intuitively that this is the case, that when I increase the number of partitions, I am lowering the amount of error that I am making. Is that understandable? Okay, now assume that instead of having 4 rectangles, I increase it to 100 rectangles. The calculation becomes messy, but of course you see that, first of all, from mathematical point of view, even though the calculation becomes lengthy and boring, but it is simple. It is elementary calculation, yes? None of these calculations are hard. So if I increase the number of partitions, so I have to work with smaller numbers, but then I put that numbers in that function. Calculating this is super simple, and then adding and multiplying things are very simple. So I will be able to get a better and better approximation. Yes, is that clear? Okay, but when do you think I will reach to the exact value? If I want, actually this is the way that we define the area. But for in this high school level, I assume that you have an intuitive feeling of what an area is, and now we want to target to find that. Okay, so when do you think in practice I will reach to the exact value of the area? Of course, if I do it with more and more rectangles, I am getting better and better approximations. But hopefully you agree with me, I will never get to the exact value unless I do it how many times? Infinitely many times. So if I can do it, of course, then the problem is that when I want to do it infinitely many times, even if you have the best supercomputer in your hand, it is not possible to do that, because if you want to do something infinitely many times, no matter what is the speed of your computer, you need infinitely many hours. Yes? So, but then let us see, is it somehow possible finally to get the exact value? Yes? So what I'm trying to say is what we have done. If I want to write a formula for this, now here I have divided the interval to 4 parts. Now assume that I divide the interval to n parts. Okay, so let me divide the area, partition the interval into n sub-intervals. Okay, can you help me to write a formula for this? So I want to partition my interval into n sub-intervals, and then I want to write an approximate value for my area. Okay, please help me to write this down, because if you know how to do this, then you will learn everything that I'm talking about. Can you write the formulas for me? Let us do it together. Here I have divided my interval from 0 to 2 to 4 parts. Okay, now my goal is to divide it to n parts. Okay, when I divided the interval to 4 parts, the length of each sub-interval is 0.5. How did I get 0.5? I divided 2, which is the length of the total interval, by 4, and I get 0.4. 0.5. Now, the length of my interval is still the same, but instead of dividing it to 4 pieces, I want to divide it into n pieces. So what would be the length of each one of these sub-intervals? What is that? Yeah?
2 divided by n.
2 divided by n, yes? So then it means that, do you agree, you see this number 1 over 2 will be, what was this number, by the way? 1 over 2 was another name for 2 over 4. Because 2 was the length of my interval, and I divided it to 4 pieces, then I simplified that, it becomes 1 over 2. Now in this case, I have the length of my interval to be 2, and I divide it to n equal pieces this time. Yes? So the width of each one of these sub-rectangles would be 2 over n. Yes? Okay. So this would be 2 over n. So can you tell me what would be the height of the first rectangle? What would be the height of the first rectangle? So you see, the only thing is that this interval is smaller. So what happens? The height of the first rectangle is still the same. It doesn't matter, yes? Because I told you that I want to take the minimum value on each interval. So the height of the first rectangle is not affected by the length of this subinterval. That is the minimum value. Is that understandable for everyone? Yes? So okay, so then it means that what I have to calculate is actually f of 0. Let me write it in this way. F of 0 multiplied by 2 over n. Do you agree that this would be the area of the first very narrow rectangle. Yes or no? Yes? Yes?
Yes.
Okay, now tell me what is the area of the next rectangle. Tell me what is the width of the next rectangle. What is the width? It's still 2 over n. Yes? So the width is still 2 over n. Yes? But can you tell me what is the height of the next rectangle? The next rectangle, for example, starts from here. You need to find the minimum and then you make this rectangle. Yes? Yes?
F of 2 over n.
F of 2 over n, because this is 0. If I ask you what is the next number here, what is the next number here, is 2 over n. Do you agree? I have divided this subinterval to this n equal pieces. So I start from 0. The next one is 2 over n. And then I have to put this number into my function to find the height. Yes? So then it means that this becomes f of 2n. Okay, and if you can tell me the next one, then it means that you understand the process. Okay, now can you tell me what is the area of the next rectangle? Okay, so what is the width? It's still 2 over n. So let me write 2 over n. But can you tell me f of which value? F of which value? So let me ask you the question. What is the number corresponding to this point? This was 0. This was 2 over n. What is this one? What is this one? Do you understand what is going on? Yes?
4 over n.
Yes, Ruben?
Oh, 4 over n.
4 over n, because each one of them has length 2 over n. Here I have one length, so it is 2 over n. The next one I have two lengths, so it is 2 times 2 over n. So it is 4 over n. Yes? So then it becomes f of 4 over n. So let me ask you the next one as well. Can you tell me what would be the next one? So the width is still 2 over n, but what is this one? Can you tell me what is this one now?
6 over n.
6 over n. Yes? Okay, and then can you tell me, if I continue this process, what would be the area of the very last rectangle? What would be the area of the very last rectangle? The width is still 2 over n, yes? Okay, can you tell me f of which value? Yes?
I'm not sure, but n minus 2 over n?
No. N minus 2 over n, you said this?
Yeah.
No. Because you see, the pattern will continue. Instead of 0, what can you imagine? So here, I am going in steps of 2 over n. So if I go in steps of 2 over n, I will not reach to n minus 2 over n. It should be a multiple of 2n. Because the first one is 0 times 2 over n. The next one is 1 times 2 over n. The next one is 2 times 2 over n. 3 times 2 over n. And then I continue to the very last step. How many intervals are there? So it would be, so can you tell me? Yes?
Wouldn't n times 2 over n, but then it's simplified, so just 2.
Okay, so somehow 90% you are correct. So you said n times 2 over n, and it simplifies to 2.
Yeah.
But there is a flaw there. Because if you say n times 2 over n, and that is 2, you are considering this height of the rectangle. But we want to consider the previous one. Yes?
2 minus 2 divided by.
No, what Kevin said is more or less correct, except with one very small flaw.
But it can't.
No, this is
Yeah, that's true.
no. This is a mistake. Can you fix it yourself?
Uh,
You said n times 2 over n. Because when you say n times, so you see this is the first rectangle, but it starts from 0. This is the second rectangle, it is 1 times 2 over n. This is the third rectangle, but it is 2 times 2 over n. Yes?
So is it n minus 1?
n minus 1. Yes? That is n minus 1 times 2 over n. So don't get confused, you see. So let me just draw the picture here. So I have 0 here. What is the next number coming is 2 over n. What is the next number coming is 2 times 2 over n, which I wrote 4 over n. What is the next number coming is 3 times 2 over n. Agree? And it will continue. How many rectangles you have? The last number is 2. The previous number is, so this 2 is nothing except n times 2 over n, as Kevin mentioned, yes? 2 is n times these subintervals. But I am concentrating on the previous one. So the previous one is n minus 1 times 2 over n. Yes? So I hope that you agree with what I have written here. Is that okay? Now, can I write it as a sigma? I want to write this sum as a sigma. So this becomes sigma. Okay? You see that I have 2 over n everywhere. So let me write 2 over n here. But then I can write f, and then I would write I, for example, minus 1 times 2 over n. Then I will run I from 1 to n. Do you agree? So let us check. If I put I equals to 1, this becomes 0. F of 0 times 2n gives me the first term. If I put I the next value, which is 2, 2 minus 1 is 1, times 2 over n is f of 2 over n times 2n. If I put I equals to 3, then I will get the next one. If I put 4, I will get the next one. So what I have written is the same thing, written more compactly. Yes? Is that understandable? Yes or no? Okay. But this is a still approximation. But if I want, I don't know if the idea works or not, but try to see that. If I want to make the value exact, what I am supposed to do, I need to make the partitions infinitely many. Yes? So this means that I expect that the real area is this sum but when I take the limit and send n to infinity. This is actually intuitive idea. It might be practical or not. But for the time being, I hope that I made this formula plausible for you. Is it plausible? That if I am able to calculate such a complicated limit, what I get is sensible to say that this is the area that I am looking for. Is that right or not? Yes or no? Okay. But now let us see if this is practical in this case or not. Let us try to calculate this limit. Because everything you need, you really know. So let us try to calculate this limit. So for calculating this limit, what is the main problem in front of me? First of all, let me write it a little bit better. So here, f of I minus 1 times 2 over n, because here I am working with this function here, yes? My function is f of x equals to x squared plus 1. I want to calculate f of this input, yes? So what I have to do, I have to replace the x with this input. So what happens, this becomes I minus 1, 2 over n totally squared plus 1. And then I squared each part here, so this becomes I minus 1 squared times 4 over n squared plus 1. Yes? So this is f of this. So this is this part of this sigma. I have calculated here. Agree? And then I have to multiply it by 2 over n. So this means that f of I minus 1, 2 over n, multiplied by 2 over n, I have to multiply this by an extra 2 over n. So what happens? 2 over n will be multiplied here. So this becomes 8, I minus 1 squared. This will be multiplied here. So this becomes n cubed. And then I have to multiply 2 over n here as well. Is that clear? So I calculated this one and I multiplied that by 2 over n. So this is the internal expression for that sigma. So now what I want to calculate is the sigma if possible. Okay? So sigma I goes from 1 to n of f I minus 1 2 over n times 2 over n becomes equal the sigma of this expression. Yes? So if I can calculate this sigma, from that expression I should be able, hopefully, to take the limit and send to n to infinity. If I can do all these things, then I will get the value for the area. But let us try to see if we can calculate this sum. Yes? So this sum is not that hard. Yes? If I want to calculate this sum, what I do, I like it like this. I write it like this. I can expand my sigma for this one and that one. So this becomes 8 over n to the power of 3. I put it out from sigma. So sigma I goes from 1 to n. Then I have I minus 1 squared. Yes? And then I will have plus another sigma of 2 over n. I goes from 1 to n. Yes? So because this is a sum, I can break my sum over to a sum over this term plus a sum over that term. Yes? Okay, but how many, I am adding 2 over n, how many times? N times. Yes? So this becomes just 2. Yes? Okay, so if you don't like this, let me change my method. So let me just do it a different way. So let me expand this sigma for the time being. So if I want to expand this sigma, I need to put I equals to 1. So this becomes 8 over n3, 0 to power 2. I am intentionally writing this 0. But this does not depend on I, so there is no I part here. So it becomes 2 over n. This is the first term when I put I equals to 1. I put I equals to 2, then what happens? This becomes 8 over n3. If I put I equals to 2, this becomes 1 squared. And then I will have again 2 over n. The next one becomes, let me put another one, 8 over n to the power of 3. Instead of I put 3 this time. So this becomes 2 to power 2 plus 2 over n. And then finally I continue this method and I will reach the final step. Instead of I put n. So this becomes 8 over n3, n minus 1 squared plus 2 over n. So let me ask you, is that understandable what I have done? I have expanded the sigma in this way. By putting I equals to 1, writing it down here, this is the whole thing. And then I put I equals to 2 and I wrote it here. And then I put I equals to 3, I put it here. And then I continued, finally I put I equals to n and I wrote it here. Is that understandable? Okay, now I want to simplify this expression. Can you help me to simplify? If you want to simplify that, what do you do? So the 2n here, another 2 over n here, another 2 over n here, and finally another 2 over n at the very end. So how many 2 over n's are there? How many of them are there? N of them. So this becomes n times 2 over n. This is taking care of these terms. Yes? But the point is that here I have 8 over n3, 0 to power 2. 8 over n3, 1 to power 2. 8 over n3, 2 to power 2 continued on that. So I can take 8 over n3 out. Then I will have 0 to power 2, 1 to power 2, 2 to power 2, and then continue until n minus 1 to power 2. Yes or no?
Yes.
Yes? Are you enjoying the calculations or not? Yes? Okay. Now, in Math 5, you learned something for this. Do you remember? This one is easy. What is the answer to this, everyone? What's the answer?
2.
2. But for this one, we learned a formula in mathematical induction. You don't have it in mind, no worries. I will write it here for you, okay? So here, we had this formula that if I have 1 squared plus 2 squared plus 3 squared, and if I continue until n squared, the answer of this sum, you prove using mathematical induction, that this is n times n plus 1, 2n plus 1 divided by 6. Yes, I can use this formula to sum this up, yes? Because 0 to power 2 doesn't play any role, so I can just ignore that. 0 to power 2 is 0. It seems that I am adding the squares from number 1 up to n minus 1. So this n minus 1 is playing the role of that capital N. So instead of that capital N in that formula that we proved using mathematical induction in Math 5, I will be able to get this sum. So let me just do that. I have 8 over n to the power of 3 outside, yes. And then instead of this sum, I use this formula by changing n to n minus 1, yes. If I do that, the first one becomes n minus 1. The second one, n plus 1, becomes n. And the next one, 2 times this number plus 1. If I multiply this by 2 and then add 1 to it, it becomes 2n minus 1. Yes? And then I have a 2 at the end. Is that right or not? Yes or no?
Should it be divided by 6?
Yeah, divided by 6, thank you. Thank you. Okay, and then you see that this n and that one of these n's are simplified. And this 8 and 6 can be simplified. So 4 over 3 n squared n minus 1 2n minus 1 plus 2. So what I have done so far, I have calculated this sigma. I haven't done the limit part yet, but I was able to find a formula for this part inside. Yes? I can still simplify it a little bit more. Just a little bit more, few steps. Let me write 2 first to make it more beautiful. And then I have 4 over 3. And then I break this n squared to 2 n's, n times n. Give one n here, give another n here. So this becomes n over n, n minus 1 over n, multiplied by 2n minus 1 over n. Agree that I can write it like that. And then I divide this n by n, this by that, so it becomes equal to 4 over 3. N divided by n is 1 minus 1 divided by this is this one. And then 2n divided by n is 2 minus 1 over n. Okay? Understandable here? Okay, now can I calculate the limit? Can you calculate the limit for me now? Because I did the hard part for you. I calculated this sigma and make it more or less a very simple formula. Then what we are supposed to do, I am supposed to calculate A by calculating the limit of this expression, then n goes to infinity. But this is very simple. Just tell me what to do. What is the answer? If I send n to infinity, what will happen for this? Yes?
If n goes to infinity, then any number divided by infinity approaches 0.
Yes?
So
it means that if I ask you what is the limit of 1 over n, when n is infinitely large, the limit of this part is 0. The limit of that part is also 0. So what is left for me? I have a constant 2 here, plus 4 over 3 and then I have 1 minus 0, 2 minus 0. So let us calculate this. So it is 2, 1 times 2 is 2, 8 over 3. Is that right?
Yes.
So this is how much? 14 over 3. That is very strange because I hope that I haven't done something wrong. The reason is that this is supposed to be the exact value, yes? But in the middle I get something larger than that. This cannot happen, yes? Because, I don't know, have I done something wrong there? I hope that I haven't done because did you see something wrong in my calculations?
But 15 over 4 is less than 14 over 4.
Oh, yes, that is 14 over 3. Yeah, thank you. Thank you. So I haven't done something wrong. I was reading it 14 over 3. 14 over 5. Now, that's probably correct. So, you see, it is a very, very long calculation. But it was practical. Let me draw your attention to some very, very important points. So this calculation is the way, because this was practical, because this was a very simple function from the beginning. Let us see, if I change this function to a complicated function, what will happen? Up to here, everything will be the same. Yes? But the point is that if this function is complicated, when I want to calculate this part here, this becomes very complicated. And then when I want to put it in the sigma, I will face a sum that I don't know any formula for that. Here, the reason that I succeeded to do this, because I was able to get rid of these dots by a formula that accidentally we had in Math 5. But assume that I make this function complicated. Everything here will be the same up to here, exactly identical, no difference. But when I want to calculate f, instead of getting this expression, I will get a complicated expression. And when I put it in the sigma, I will get a complicated series that I don't have any formula for that. So that would be a dead end. Even though, so it means that it was practical, possible for this simple function, but don't expect that this method will work for any kind of functions. And I want you to be able to detect the error, to detect the problem. The problem is that this sum becomes complicated and I don't have any formula for that. So then it means that I have to stop there. Okay? But here I was able to continue because I had this series is a nice one and I had a formula for that. So don't expect that this method will work for all possible functions, because I want to tell you the Newton's method. Newton realized that instead of going through this mess, you can do one simple step. Now this is the real connection between the area and primitive function. He realized instead of doing this, find a primitive function for your function. Is it hard? No, it's very straightforward. So that's a matrice problem. Can you tell me a primitive function for that function? X squared plus 1. What is a primitive function for that? Just tell me. One primitive function is enough. X to the power of 3 divided by 3 plus x. Yes? So that is a primitive function. But now Newton, so what is the interval of interest? The interval of interest is from 0 to 2. Newton said that, okay, you calculate f at 2, the endpoint. You calculate f at 0. You calculate f at 2, what happens? It becomes 8 over 3 plus 2, which is 14 over 3. And you calculate f of 0, which is 0. And then subtract them. So this is Newton's method. And this is the original method. Yes? So this number that you get here is exactly this number that you get after this very long calculation. Yes? And now the point is this. This method is really superior to this method. Why? Can you tell me why? Because even if I make this function complicated, more complicated than this one, as far as you can find a primitive function for it, you can do this method. But that method will actually stop there. You cannot do that. So it means that this is not just something, this is a huge progress. Not only you can solve the problems that you could already solve with this mess and lengthy calculation, but you can also calculate things for functions that you really don't know how to calculate using this because you don't know how to calculate the sum. Is that understandable? So it was not evidently seen the connection between this idea and the connection between the area. So he discovered that instead of doing this, we can do this. Is that understandable? Okay, so this I want you to see and feel it. There are some versions of this in the book as well, but don't worry about doing the calculation like that unless you really like to do it yourself. But I want you to see that if you should appreciate the Newton's work because you see that this is very, very simple compared to this lengthy calculation that we have done. Is that clear? Okay. Now, let me also demonstrate some GeoGebra here for you. So there are some internal functions, I think, in GeoGebra that you can produce these things. And there are some exercises in the book that probably you need to use GeoGebra to solve them. So let me pause this recording for a moment. Okay, so here, let us try to understand this, that I want you to feel that it really works. It is not just a fancy calculation. I think you will feel it now. So here, if I remember, the command is lower. Yes, you see it's called lower sum. Because do you remember, when I wanted to do this area calculation, I told you that find the minimum value of your function and make your rectangles. So all those rectangles are below the curve. Yes? But you can choose the maximum value. And some parts of those rectangles will be beyond the curve. But in the limit process, all of them will go to the same number. So this is why in GeoGebra, as you see here, I just typed lower and then suddenly it appears. And then you see that here you have lower sum function, start value, end value, and the number of rectangles that you want. Yes? So here, what was my function? My function was x squared, yes, plus 1. So I typed that function here. And then what was my starting value? Can you tell me? What was the starting value? No, the starting value on the x-axis. 0. And then what was the final value on the x-axis? How much? 2. And then let us calculate, for example, how many rectangles. Let me consider 4 rectangles. So you see that I have it here. Yes? And let me also draw the graph of y equals to x squared for you. So why this
Plus
is...
1.
Okay, so that is plus 1. So this is the value that I get. And this is what, this is 15 over 4. Do you remember 15 over 4? We got it for 4 rectangles. So this number that you see here on GeoGebra is the sum of the areas of these rectangles. Is that understandable or not? Yes or no?
Yeah.
So that was the graph that I drew it for you from 0 to 2. Do you remember that portion of the graph? And then I am making these rectangles as I did in my calculation, and I calculated this actually for you. The answer that I got, if you remember, was 15 over 4. And 15 over 4 is exactly 3.75. Is that clear? And now I want to increase the number of rectangles. For example, from, can I make it a little bit bigger here? Let me see. So let us concentrate on this part. Yes, that is better. Yes? And now let me increase the number of rectangles. This 4 is the number of rectangles. So let me make it 40. Yes? Let us see what happens now. So I will get this. So you see that the errors that I am making are these white parts. The sum of all these white parts is the total error that I am making if I keep 40 rectangles. I hope that you agree with me the sum of these white parts is smaller than the sum of the white parts for the 4 rectangles. But it's just 40. So let us make it, I don't know, 400. Who cares, yes? It's more or less continuous. So probably with your eyes you cannot detect the difference between this and the area, the real area. Of course, if I zoom in, I don't know how much I can zoom in, probably we should be able to see the errors. Yes, you see the errors are there still. These errors you see, these are small parts. There are some errors there, but this is probably good enough for us. Yes, so let us zoom back. And then hopefully you agree with me that if I make it 4,000, I don't know if it can calculate, yes, it's more or less a continuum, yes? So you cannot differentiate. Now this is just 4,000, make it 4 million, make it 4 billion, and then make it infinity. Yes? So that is intuitively, hopefully you agree with me that this method in principle works, but we have some practical problems when we want to really calculate the exact value. Because for the exact value, I have to do it infinitely many times. Yes, is that understandable? Okay. So at least you can see this will work. So now that I am here, if you don't mind, let me also show you at least the upper sum. The lower sum is based on the minimum value, but the upper sum is based on the maximum value. So let me just try to do that one as well. So let me get rid of this. Okay, so here I would say upper sum. Yes, you see something similar for that. And then I have x to the power of 2 plus 1. And then starting value was 0 again. The final value was 2. And let me make the rectangles for the time being. Let us make the rectangle first equals to 1. So let me see, could you expect this? Let me tell you what is happening. Yes? So this is my function. When I put the rectangle equals to 1, I need only one rectangle. So it means that the whole interval from 0 to 2 is divided to one part. And then on this interval, instead of finding the minimum, I find the maximum and construct the rectangle. So the area of this rectangle is more than the area that you are supposed to calculate. Yes? But again, so if how much is the error? The error is this area, because this area I don't want it, but I have calculated it. So I have to throw it away to find this one. So that is the amount of error that I have made. Yes? But now, let me make it 2 rectangles. Then what happens? This is for 2 rectangles. I want you to be able to imagine it. Why 2 rectangles is of this form? Because from 0 to 2, I divided it into 2 parts. And then on this interval, I find the maximum value and I construct the rectangle. And then on this interval, I find the maximum and construct the rectangle. And I hope that you agree this time, the sum of this and that is smaller than the error that I made before. And for the same reason, if I increase the number of rectangles, I'm always getting something more than the real value. In the previous case, I am always getting something lower than the real value. But then if I go to 20, for example, you see that still I am making some errors. The values are above the real value, but it is becoming closer to the real value. So it doesn't matter, you see, if I go to 200, for example, then you more or less see the same thing. So in the previous case, always my estimates are lower than the real value. Each time I am increasing it to the real value. But here my estimates are always above the real value. By increasing the number of rectangles, I am making them smaller to the real value. That's the difference. But it doesn't matter, it doesn't matter if you use the upper rectangles or upper sums or lower sums. Both of them will approach the same thing if my function is, of course, a well-behaved function. And well-behaved here means continuous. So if you have a continuous function, that will always happen. And by the way, you can also choose any random number in that interval. That would be a little bit more advanced. But all of them will approach to the same value, and that value we call the area. Any questions here? Is that understandable? So the take-home lesson for today is that, okay, this limit that I wrote on the board is an important limit. Yes, at least it appears when I want to calculate the areas. Yes? Okay, now let me pause the video and go back. Okay, if you don't have any questions, I think it is good to stop here, and then we continue the next lesson. So, I want to tell you, what is important from all these things that I have given you is to see that what we will learn, and mostly all the time I would say, we will use Newton's method, but I want you to see that Newton's method is actually really worthy to learn, okay, because it is actually, helps us to get rid of all these calculations, and sometimes it can also calculate the problems that we cannot solve using this crude model. Okay, any questions?